In this video, I'm going to discuss describing motion in one dimension, and I'm going to specifically talk about position and velocity graphs as well. So we've defined position, like for example, you can have a number line and we can call it, let's say, the x-axis, and so we could name every point on this line with a number, and we can give the position of somebody or something with simply giving the variable value. So if somebody was standing here on the 2, we know that we would say their position is x equal 2. And then we also saw that we can talk about changes in position, and that was how fast the x changes. We write that as delta x divided by how long it takes you to do that. And then we said that speed was the absolute value because we want speed to always be positive. Okay, and there was some difference between length and displacement. Displacement was delta x, but length or distance is always the absolute value of delta x. All right, now what I'd like to do is talk about graphs. And so you can describe motion with algebra equations in terms of v and x, but sometimes graphs are useful, and you're going to want to be able to switch your brain to thinking about that. So let's start with some examples. So suppose I gave you the position of something, and suppose that I said that it was, the position was the line that went something like this. Let's do a red line, and then let's have another example on top of that, the purple line, and then let's have another example, and let's put some numbers, and then let's see if we can describe what's going on here. Alright, so let's do the red example first. So the red line first. So I would say that the red line is describing a motion on the x-axis. So let's draw an x-axis from 0 to you know what, let me also, to make it clear that x and t are not the same, let me change the values. Okay, so, and then let me emphasize that what these endpoints are. So we'll call this 3, 6, 3, 3, 1, 2, and let's ignore the, actually, you know what, let's not focus on where they intersect. That's not so important. Okay, so the way that I would describe the red motion, the graph, what that motion represents, is I would say that something went from x equals 0 to x equals 6, and it took 3 seconds to do it. Okay, so somebody was at 0 and then they walked to the 6, and it took them 3 seconds to do that. You can even get the velocity. Okay, so 6 minus 0 over 3 minus 0, and it's 2. Let's give some units. Let's say meters in seconds, so 2 meters per second. All right. Notice that the velocity is the slope of the red line. Okay, that's an important observation. That's a handy thing to know. In fact, I'm going to type it. It's so important. The velocity is the slope of the of the position versus time graph. Okay, so make sure you got that. Now let's do the purple. What's going on with the purple? So imagine there was a purple guy standing at the x equal to 3, and what did he do? He didn't do anything. For 3 seconds, the purple guy just stood there, and that's it. Okay, notice that the slope of the purple line is 0. So that means that the velocity is 0, which is what we would expect if he's not moving, he or she. Okay, so that goes along with that. And then the green is somebody that went from x equals 3 to x equals 0. So it was, let's see if we could draw that one. It was, so somebody was standing here where the purple guy was, and then they moved from 3 to 0. They moved it to the left. Okay, so we could calculate the velocity of that one as well. So velocity is final minus initial of the chain, the delta is final minus initial. So the velocity that I have there on the board, that one was the red. So let's let me first label that one so we can not get confused. So that's V sub red. Now let's do V sub green. And so final x minus initial x. Notice the order is very important. Final time minus initial. And so that gives minus 3 over 3, which is minus 1 meters per second. Okay, so notice the first velocity, the red velocity was 2, and the green velocity, the velocity associated with the green line is negative. Okay, I notice that the green line has a negative slope. Okay, a negative slope of minus 1. So again, the velocity is the slope of the line on a position versus line graph. All right, very good. Now let's look at some velocity graphs. So each of these motions, we've already calculated the velocity, so we're not surprised that they have a velocity. Let's now graph. It might not have occurred to you that you could actually graph the velocity versus time. So let me move some of our work here, and let me shrink our graph, and we'll see if we can graph the velocity versus time. Okay, so let's do it, and I'll try to color code it the same as, well, you'll see. So here we have time in seconds, and this time notice the vertical axis is going to be velocity, not position anymore. Okay, and we'll go 1, 2, 3 seconds, and we'll do 1, 2, minus 1, minus 2. All right, let's ask ourselves now, the graph of position, the red line on the x versus t graph, that had a velocity of 2, and the velocity of 2 was for the entire 3 seconds, right? So we're going to graph the first 3 seconds with a horizontal line. Why is it horizontal? Because a horizontal line keeps the y value, the vertical value, keeps the velocity constant. Okay, the variable associated with the vertical axis, that has a constant value. All right, and then the purple, we said, had a velocity of 0, zip, and that one was, so we'll do 0 for 3 seconds, so that purple line will rest on the horizontal axis, like that. And then the green is, that one had a negative 1. Okay, so a negative slope on the position versus time graph will give us still a horizontal line, but it's below the horizontal axis. You see that? Okay, so those are the velocities graphs that correspond to the position graphs. Okay, now so far I've done velocity graphs that are constant, they're horizontal. Is it possible to have velocity graphs that are not constant? Yes. Let's finish by discussing what that means. Okay, so I'm going to go to a new whiteboard now. Okay, so we know what it means to have a constant velocity. That's something cruising at that's some speed. Okay, now if we had a increasing velocity function, let's think about what that means. All right, so, and let's see if we can imagine something that moves like that. Okay, so that would mean that the velocity as well as the speed was increasing. All right, what would be something that moves like that? How about there's a car at a red light, the red light turns green, so you press the gas pedal. Don't you start going faster and faster? You don't instantly get up to your cruising velocity, right? It takes some time, right? So this would be maybe you're working your way up to the velocity that you want to maintain. Okay, if you wanted to describe more of the time, more of the behavior for more time, let's say you got up to some velocity and then you kept cruising at that velocity, which can you see that from when you get to the desired velocity, you would, after that, if you maintained it, can you see that the graph would then become a horizontal piece like that? Okay,